Okay, so for the sake of it, we're just asked to find, okay, a way to simplify this expression here. We have an equation, okay, that apparently results true for all values in the domain, okay, so the domain is from negative infinity to positive infinity, okay, so we have something very, very peculiar here. We have the initial height, okay, times the integral of force dt. It reminds us of something very important in physics, okay, the integral of force over some, okay, distance, delta x, okay, is going to be, okay, imagine this is an arbitrary curve, it's going to be the area below this curve. So the area below this curve is essentially the work done by this force. And right over here we have equal, okay, to sine inverse of x. And we're told that, okay, x is sine of j degrees. And that's multiplied by the integral from 0 to 1 of ex dx. And we're going to add the derivative of momentum, first time derivative of momentum squared, okay? So we're going to see how this is going to turn out. This looks like a very hairy equation, okay? It looks like something you wouldn't want to, you know, even try simplifying, but let's see what we can do over here. So on this side of the equation, well, we know that the integral of force dt from 0 to x is going to be the work done by the force over some distance, right? So this is essentially, okay, the height multiplied by the work done, okay? So that's going to be equal to sine inverse of x. Okay, in this case, sine inverse of x, if we think about it, you do sine inverse of both sides. Sine inverse of x is going to be j degrees, okay? So j degrees, so we got j degrees times the integral from 0 to 1 of ex dx. And what's the integral from 0 to 1 of ex dx? It's very trivial, right? It's just ex from 0 to 1, which is essentially e to the 1, right, minus e to the 0. And e to the 0, we know that's going to be 1. So let's just get rid of that. We don't need that for now. And then we're going to add the derivative, first time derivative of momentum. What's the first time derivative of momentum? Do you know that? Well, let's see. Momentum is equal to, okay, mv, right? And then if we take the derivative with respect to time on both sides, well, what do we get? Mass is a constant, right? Unless you're like, you know, eating really, really like a lot of food every day, you're going to get fat. So the mass is going to increase and it's no longer constant. So, but in this case, we're going to assume that mass is constant, you know. So it's like a perfect condition. And then velocity, of course, velocity could change. So imagine that this person moves all the time, and essentially nothing is, standing still. Like Newton said, you know, an object at rest remains at rest, and an object in motion remains in motion. But in this case, okay, we're going to assume there is a change in velocity. So we're going to take first the time derivative of velocity, and that's going to be acceleration, right? So p is equal to ma. All right, d over dt of p is going to be ma, and then we're going to square that. So if we square that, that's saying m squared a squared, right? So that's going to be m squared a squared, all right? And then over here, we could rearrange this a little bit. So we're going to have something like this. So we're going to have the work done times the initial height is going to be equal to the degrees, j degrees, times e plus m a, right? And maybe we could rearrange this a little bit to see what we could get, okay? So let's see if we rearrange this a little bit and see what's the hidden message. Maybe there is something in here. I'm not sure, right? Well, I think we're done for now. I'm just going to continue doing some interesting integrals. So I'll see you later.